Given the rate that the human population has increased here on Earth, it makes a lot of sense to try and determine the progression of development, past to present, in terms of physical build-out in different locations. The information that we gain from such studies could help guide us towards greater sustainability in the future. This is certainly the case when it comes to urban growth. Philippe Labadie's project analyzes urban growth in the Tucson metropolitan region from 1998 to 2010 to determine where and how urban growth is manifested. One nice thing about this project, one nice thing I think about this project is that Philippe is using a certain kind of high-resolution data that hasn't been used in projects of this sort in the past. So that's a really nice wrinkle to this project. So let's see what you've got for us, Philippe.
Thanks, John. Okay, so the title of my project is Quantifying Urban Development in the Tucson Metropolitan Region. The presentation overview. So the presentation has been organized in the following format. I'm going to introduce the project area and goals, and then we're going to discuss the conclusions before we open it for questions. So the introduction. The study location is the greater Tucson Metropolitan Region. It consists of Marana and Oro Valley to the north, the city of Tucson in the center, and Sahuarita to the south. Increased population growth in this region has mainly taken the form of sprawl, or low-density development, far from the original urban core with non-functional open spaces. A recent shift in regional planning is to focus on development in close proximity to the existing urban infrastructure. Identifying the amount and locations of new urban development is important in this planning context. So here's some population statistics for the time period. The population of Pima County increased by over 157,000 people between 1998 and 2010. 73% of this population change of Pima County occurred in the Tucson metropolitan region. This emphasizes the importance of this urban region for the county as a whole. Here we can see the boundaries of our study sites in 1998. At the top in purple is Marana. Next to it in turquoise is the Tortolitas, and in orange is Oro Valley. In the center in pink is the city of Tucson combined with the city of South Tucson. And at the bottom in rust is Sahuarita. On the following slide, I'm going to present the 2010 study area. Okay, so at the top we can see that Marana has grown significantly towards the north and the east. Up here. The Tortolita site has been mostly annexed into Marana and Oro Valley. As you can see, it's no longer in between. And I can switch back here. So you can see Marana has really grown to the north, and then it's annexed this portion of the Tortolitas, and Oro Valley is annexed this portion of the Tortolitas, and the rest is just now unincorporated Pima County. In the center, we can see that the city of Tucson has grown to the south. Oops. Right there. And we can also see at the bottom that Sahuarita has grown significantly to the south and the east. So it's pretty small here, and then it really balloons. Okay, so the goals of this project is to quantify the amount of urban development from 1998 to 2010 for the study region, identify topographic variables underlying this urban change. We're going to use conventional desktop computer with ArcGIS 10.4 and IBM SPS softwares for processing and statistical analysis. The use of 1 meter high resolution imagery provided the study with higher accuracy over the more commonly used 30 meter imagery like Landsat, MODIS. Lastly, to continue the work of integrating the fields of remote sensing and GIS for urban studies. Okay, so here's the project overview for the workflow. There's basically five main steps in the project overview. Each one of these steps obviously has more processes to it, but this is just collapsed. So it's mainly supervised classification, post-classification change analysis, a land use change detection algorithm, thematic mapping, and then regression analysis. So the first part is quantifying new urban development. I am using supervised classification. This is an iterative process, and the error accuracy assessment determines whether or not we move on to the next step or we have to start again. After it passes, the new raster is reclassified. It's a binary schema, so it's urban land use or it's vegetation or bare earth. And then we have a post-classification change comparison to determine the new urban land use and acreage. So the land use land cover supervised classification For this project, I used two digital ortho, quad, or quad images. The first image from 1998 is obtained through Pima County Association of Governments, or PAG, and the 2010 image was obtained by the United States Department of Agriculture's National Agriculture Imagery Program, or NAPE. The supervised classification using separate training sites for each image was conducted. That's because the anniversary dates for the two images. The first image, I don't know when it was collected, but it definitely didn't match the second image, and you could just tell that by shadows. The imagery was successfully classified into urban or bare earth vegetation when the overall accuracy exceeded 85%. Additionally, acceptable user's accuracy and producer's accuracy, as well as the kappa confidence levels. So I used Jacob Cohen's. He had a work in 1991. It was actually for psychology, where he introduced the confidence for the kappa. And it's kind of just a 0 to 1 scale, so 76% is pretty moderate. And Russell Congleton, he kind of pioneered some of the overall accuracy, as well as really looking into user and producer's accuracy. And so his benchmarks are greater than or equal to 85% for an overall accuracy, and preferable that you have your users and producers accuracy greater than or equal to 70%. Okay, so much of the misclassification appeared to be due to the different anniversary dates I was mentioning earlier, and it took two forms. So one of them is changes in vegetation. They can either conceal the land cover classification underneath it, or vice versa, the tree is cut down or whatever, and now there's something showing. And the largest one, which apparently plagues most urban analysis using remote sensing, is shadows. And so in addition to having shadows, which are difficult for the supervised classification algorithm to determine, you have different anniversary dates, so it creates shadows in different areas, so then there's a larger portion of inaccuracy. So the next step is detecting new development. We're looking at converting locations developed into point features, and the point of this is, one, to garner location statistics, but also we're going to need those points to sample for the regression. So the process begins with a land use change detection algorithm. This produces a raster that describes a from to, so from vegetation to urban, for the 1998 and 2010 period. The error accuracy assessment is still needed here because it's a form of classification, so you still need to determine whether or not it's accurate. Finally, locations are examined and statistics are derived post. I used ArcMap, so this is just creating points at these locations. So we have our land use change detection and statistics. In order to find locations developed, I reclassify the imagery into separate numerical categories of either urban or non-urban. And from the values that are derived using the algorithm and raster calculator, you can determine which locations actually change from a non-urban to an urban. So then these reclassified images were then used in a land change detection algorithm, determine the cell values. Points representing these new urban developments were created in ArcMap, and we get our location statistics. Half of the new developments occurred in unincorporated Pima County, surrounding urban centers, real close proximity, and a third of the new developments occurred in the city of Tucson. It's important to note that in our context because when we were looking at the two change maps, part of it was annexation, so it wasn't that the town of Marana was driving that growth. The growth was actually occurring in Pima County, unincorporated Pima County, and being absorbed into Marana. But since 33% of the new urban developments actually occurred in the city of Tucson, that's telling us that 1/3 of the development actually has a preference to be inside the city. Okay, so here I'm going to present a couple of examples of the post-classification change analysis for examining new urban development. So in this image, we have an example of greenfield development. You can see up in the 1998 image, we have fields here and just a big tract of vacant land. By 2010, you can see that this is a mixture now of high residential development as well as mixed commercial, and there's some apartment buildings in here. So here's our supervised classification. The black is representing bare earth or vegetation, and red is representing urban. So because this is mainly greenfield, it's mainly black with just a road and a couple little farmhouses. Now here's the land use change classification, post-classification change. We can see that a portion of that existing urban is still here, but now we have the green, which is representing new urban. And so we can see that some of the tiles, the roof tiles, are not showing up because they're too similar to the ground reflectance values. But otherwise, the whole area has basically been developed with the exception of this private land over here. So similar to the previous image, we can see here an example of development in the Catalina foothills. So the difference here is that here we have just uninhabited desert landscape, and in 2010 we have a new development, but it's low density development, rather large homes sitting on minimum of an acre lot. But this development is actually preferable in this situation because it preserves a lot of the natural landscape, which is what people who are already living nearby basically want. So in a planning context, this is okay. Looking at the post-classification change analysis, we can see here in the green, the road as well as the houses are clearly showing up. Okay, so here we have an example of high-density infill development. This is along 22nd and Prudence. And in the 1998 imagery, we have a vacant lot here, but it's surrounded by urban development. So this is a great example of Reed Ewing's definition of sprawl, which is that the growth has continued past this point, but it's left in open space, and this open space is not serving any function. It could be, open space like a park, or it could also be additional housing or commercial use. By 2010, the developers decided to build this area. It's high density development, and their homes basically sitting on 1/10 of an acre. So they're efficiently using the land. And this is preferable when referring to Pima County's Prosper's comprehensive plan. They're really trying to tackle sprawl by encouraging this form of development, and this is an example of a success, basically. Additionally, this also illustrates why the post-classification change comparison is important. As you can imagine, when you're dealing with over 300,000 acres at 1 meter resolution, finding locations that actually show that they've been developed can be very difficult. But when you are using a binary schema and then just creating a third variable to describe areas that have developed, they then stick out much more easily, and you can put points on them for sampling. Okay, so the last example here, this is an example of redevelopment. So in the 1998 image, we have the old Christopher City. It was originally designed in the 1960s as a retirement community. It failed financially, even though they were considered at the time very high efficient, all electric housing with many amenities, including recreation and like a miniature hospital, if you will. When they failed financially, they sold the property to the University of Arizona, and it was converted into graduate housing as well as couple housing. But by the year 2000, they had found that the development was plagued with black mold. The university decided they didn't want to continue to operate this property and sold it to a private developer. This private developer decided that he was going to build high density development in this area. And what we see here is that in the supervised classification, the red is representing the existing urban structures. And in the post-classification change analysis, we can see that there's significantly more green now than red, representing it's a much higher density of development. Additionally, the red is preserved because those areas were urban in their classification, urban land use, and in the 2010, those areas actually remained urban, if that makes sense. Okay, so the next step is mapping development factors. This is going to be thematic mapping. We're looking at land use change factors as well as an exclusion mask. The factors that have been considered to influence new urban development are mapped in ArcMap using tools to create sample layers. The exclusion mask is created from SQL attribute queries and location queries, and this is to prevent the analysis of undevelopable or areas that are not of interest. Okay, so areas that are created for land use change factors, mainly proximity to amenity factors, topography, private land ownership, and transportation infrastructure. And areas that we're not interested in looking at: public land trusts, major washes, parks and recreation, civilian and military airports, and Native American reservations. I have here 3 examples. So the first example is distance to major washes. It's a Euclidean distance, and the white represents close proximity to the wash, and the black represents the maximum distance calculated by the tool. This is important because washes are considered somewhat preferable to live near because they serve a sort of recreation or entertainment type amenity. The next image here is kernel density of 1998 street networks. And so in this example, transportation infrastructure is kind of a given for development because most people are going to drive cars, as well as the people who are going to be doing the construction. But additionally, it means that there's a strong urban cluster of population. And it's kind of a pseudo-demographic analysis that this project otherwise wouldn't have. So it's access to amenities as well as a large population. The last example here is slope. Slope's important because higher grades are much more expensive to develop, and after a certain grade, it's pretty much considered undevelopable. So the last step here is a logistic regression workflow. So we're going to sample the points that we identified. We're going to export them as a CSV, convert that into an Excel file, import it into IBM SPSS, run a logistic regression analysis, and we're going to get our land use trend variables out of that. So it's a step forward binary logistic regression. There's 224 observed new urban developments. I created 1,000 randomly stratified developable locations that did not develop. 81% of the dependent variables were correctly predicted by IBM software, and new urban development showed a preference for higher density of street networks, private land ownership, and lower slope. So in conclusions, the project successfully combined remote sensing and GIS for urban analysis using only a conventional desktop computer running ArcGIS 10.4 and IBM SPS software. This study reached acceptable levels of accuracy with low error rates using the 1 meter high resolution imagery. From 1998 to 2010, the project determined that approximately 5,319 acres, which, if you remember Kevin's presentation on the buffalo grass and the saguaro national monuments, the western is a little over 6,000, so it's quite a bit of development. The new urban development preferred locations with higher street density, private land ownership, and terrain with lower slope. These results are intuitive because they indicate that developments tended to cluster around existing urban areas, likely due to lower cost of development and location desirability. I have some suggestions for future improvements. LiDAR was unavailable for the 1998 imagery, as well as because of the 300,000 plus acres being examined in this study. I would need basically like a supercomputer, which wasn't available either. So I tried to maintain a lab-like setting, so I did not include socioeconomic data like a decennial census because it would not be available for 1998, and I would have to do an estimation of what type of changes in population as well as median income. And data that was available through estimates from the state and the county were not at the same scale, so it wouldn't work with this project because it was either statewide or county-wide or city-wide, but not compatible with my region. Here's my references. I'd like to thank you for coming tonight and listening to me, as well as the other speakers, and I'll open it up for questions and comments. All right, thank you.